Hi guys, welcome to the session. This is Rashekar from St. Peter's Engineering College. In this session, we are going to discuss about the Bayesian classification, Naïve Bayes, and Bayes theorem. Let's start our session. Bayesian classification. What is a Bayesian classification? The Bayesian classification are a statistical classifiers. Though in the Bayesian classification, we are using the maximum of the probabilistic predictions. That is, predict the class membership probabilities or any statistical values given by the data set will be predicted by using the Bayesian classification. There can be predicted class membership probability, such as a probability that given by the tuple belonging to that particular class. So each and every tuple belonging to that particular class will be classified by the Bayesian classification. The Bayesian classification is based on the Bayes theorem. So the main foundation of this classification is based on the Bayes theorem. So it is Bayes is one of the theorem. By basing on this theorem, will classify the values. And the studies comparing of the classification algorithms have found a simple Bayesian classification and has a comparable performance with their decision tree and the selected neural network of the classifiers. So the maximum performance of the Bayesian classification will have the Naïve Bayes classification, Bayesian classifiers, belief of the Bayesian classification. And all the things will come to the decision tree selected neural network classifiers. So here we have a Bayesian classifier has an exhibited high accuracy and the speed when applied to the larger of the data set. So when you apply a large data set, it has a high probability of the values and high accuracy values, and it performs in a very fast and it gives a better results with a classification. Naïve Bayes classifiers assumes that each and everything that affects of the attribute values of the given class, independence of the values of the other attributes, and also it comes to the assumptions of the values also come. So these assumptions are also called as class conditional independencies. So the class conditional independencies are the effect of the attribute values of the given or the independent of the values of the other attributes. So independent of the other attributes are known as class conditional independency. So it may be a simple things. So it may be a simple of the computationals involved and in the sense of the considered as Naïve Bayesian. So mainly the Bayesian belief networks are the graphical models which are unlikely Naïve Bayesian classifiers. And those are all the dependency among the subsets of the attributes. So each and every attribute is a dependency with the subset of the attributes, and it can be also used as a classification model. That is a Bayesian belief network can also be used as a classification model. Where you have an incremental of each training example can be incrementally increase or decrease the probability that you have a hypothesis is in a correct prior knowledge and can be combined with an observed data. So each and every increase and decrease of the probability will be considered as a hypothesis of the prior knowledge of the data. And we have any standard values of this Bayesian classification. The standard or even the Bayesian methods are computationally incredible. They can be provided as a standard or optimal decision making against which of the other methods can be measured. So each and everything will be verified and it can be maintained as a classification model. So here we have a Bayes theorem. So this is the Bayes theorem probabilities. So the total probability theorem will be based on the P of B is equal to M sigma I is equal to 1, P of B by AI into P of AI. So the Bayes theorem will have a probability of the H by X is equal to P of X by H and P of H by P of X. So this is the Bayes theorem. So what is the X here and what is the H here means? Let X be the data sample, there is an evidence of the class label is unknown. Let H be the hypothesis that has an X belongs to the class C, and we have to calculate the P of data sample, P of probability of the hypothesis and the data sample values will be calculated by using this formula of the probabilitical values. Those probability values of the P of X by H and P of H by P of H. So the probability of the hypothesis and the data sample will be calculated by using this formula and whatever the value resulted by this hypothesis of the data sample will be maintained, will be in the Bayes theorem of the Bayes values. Here the X considered as an evidence and H considered as an hypothesis. If X belongs to the class C, the class C will be the that class C will be the specified of the class C of the classification problems. P of H by X is a posterior probability or a posterior probability of H. H conditioned on the X. So here we have P of H is a prior probability and P of X by H is a posterior probability. H by X is a posterior probability and P of H is a prior probability, that's an initial probability. Example, X will be the by a computer regardless age, income. So P of X is a probability that sample data is observed. So X has a probability of the data is observed and H is a prior probability, that is an initial probability of the values. Where we have to calculate it with the P of X by H like as a likelihood. The probability is observing of the sample of X that given data of the hypothesis holds. Even the X values will be by so the probability of the that X is a 31 to 40 is a medium income, that is the income values will be denoted by the X. So here the prediction based on the Bayes theorem. So we have a prediction values. That prediction values will given the data. Prediction values will given the data as an X and posterior probability of the hypothesis X and P of H by X is follows by the Bayesian theorem. So the same Bayesian theorem will be reflected here and it will be calculated by the probability of the hypothesis of the data values. That is a training data. Informally, this can be viewed as a posterior is equal to likelihood into prior or evidence values. So the likelihood or prior evidence values will be predicted by using the posterior values. Here we have to predict the X belongs to Ci. If the probability of Ci by X is the highest among all the Ck by X for all the K classes. If the K classes are all highly predictable, then it can be belongs to the X. If the partially difficulty means it requires the initial knowledge of the many probabilities involving on the significant values. So if it requires the initial knowledge of the many probability values, which involves a significant computational cost of the particular difficulty. So this is the prediction of the Bayesian theorem and the classification to derive the maximum posterior values. Here we have to derive the each and every values which has a posterior and predictions and the partially inflated and the hypothesis, each and everything will be calculated. So here we have to classification to derive the maximum posterior values. Let's consider as a D be the training set of the tuples and their associated classes labels as an each tuple represented by an ND attribute vector, that is an X is equal to, that means the training set is equal to X1, X2, X3 and so on to Xn. Suppose there are M classes are available in that particular C that considered as a C1 to Cm, that is a C1, C2, C3, C4 and so on to Cm. The classification is to derive the maximum posterior, that the maximum of the P of Ci, that the maximum of the P of Ci values will be considered and it can be posted as a C of P by X. This can be derived by the form of the Bayesian theorem like as a hypothesis of the data set, hypothesis under the training data set like the M classes by X of the training set, that is equal to probability of the training set by classes and the into probability of the classes by probability of the training set. So since P of X is a constant for all the classes, only P of Ci by X is equal to P of X by Ci into P of Ci. So it needs a maximized value of the posterior values. Then you'll get the posterior of the maximum posterior values with the class and the training data set. Now, what is a Naïve Bayes classifier? Why this Naïve Bayes classifier is used in the Bayesian classification means? So it's a simplified assumption. Naïve Bayesian is a classifier or a simple Bayesian classifier works as the following below. A simplified assumption that attributes have a conditionally independent that depends on the, that is no dependency relationship between the attributes. So each and every attribute we don't have no relations with a sigma, that is a pi values So we are calculating with an P of X by Ci values by using this formula. This greatly reduces the computational cost, only counts the class distribution values only. So here we have to maintain the class distribution values. This greatly reduces the computational cost. So by using these Naïve-based classification will reduce the computational cost, and it counts the class distribution values also. Each class distribution values will be segregated by using the categorical values. So for example, if A of k, AK is a categorical, so P of xk by Ci is the tuple of the Ci having a values of x of k. For A of k is divided by CID, that the tuples will have a Ci in D. So these are the continuous values will be represented in the by using an x, mu and sigma, that is equal to 1 by root of 2 pi sigma, that gives an x value. So here the values of the shows that a maximum posterior hypothesis by using the Bayesian theorem with the P of x by Ci and the P of C by Xi. So we have a P of x as a posterior values with a maximum computationals. So given the data will set many attribute values. Given data will have to set in a many number of the attribute values. These attribute values will have to show the given data set of many attributes. It would be an extremely computational explained, and it's a compute of the P of x of C in order to reduce the computational values. In order to reduce the computational values will be presented in the Naïve-based classifier, which gives a distribution of the mean on the mu sigma and the standard deviations of the sigmas. So this is the example of the data set given by the Naïve-based classifier. The same data set of the decision tree what we took in that is the age, income, student, credit rating, and the company name. If class C1 is equal to biased computer means yes, and C2 is biased computer means no. That means we are giving a class labeling, that is the tuples of the values will be given as a yes or no. So the data is to be classified by using the x is equal to age less than or equal to 30 or greater than or equal to 30 or equal to the 30. That means we are giving a data is classified x is equal to less than equal to 30, income is equal to medium, student is equal to S, credit rating is equal to fail. So by basing on these values, automatically the base classifier will identify where the candidate, that is where attribute are less than 30 and the where income is a medium, and if the student is yes, then credit rating is a fail. If all these specification rules are satisfied, then only it will accept the classification. For example, you consider here, you look on here, P of Ci is equal to P bias computer is equal to S, that is equal to 9 by 14, that is equal to 0.65. Why 9 means only here you have took the data set, here S are 9 and no's are 5. So 9 plus 5 is equal to 14. Here we have a total attributes are the 14 attributes, and 9 are the S values and 5 are the no values. Now P of by computers is equal to S. So S values are the 9 by 14 is equal to 6.0643. That is a P probability of the values, and P of the no values are the 0.357. So here we have an S category having more values. Then compute the P of X by Ci. That is compute the training data set by the class values for each class. P of age less than or equal to 30 or by a computer S. So whose age is less than 30 and computer value they are ready to purchase the computer means S means there are only 2 members with the probability of the S of the 9. So 2 by 9 is equal to 0.22 and less than equal to buy a computer no 3 by 5. Why? Because no's are the 5 only. 5 or the buys computer. Those candidates are want to buy the computer means only 5. So 3 by 5 is equal to 0.6. The probability of the values is n as 0.6. Like this, we will calculate all the income is equal to medium, income is equal to medium. If student is yes, we'll calculate the S and no. If credit rating is fail, calculate the S and no. If you calculate all the things, the values will be like this. So if all the categorical values are separated by using this 0.22, 0.6, 0.44, age less than or equal to 30 will have a 0.2 in S, age less than or equal to 30 with an no values are the 0.6. So if you calculate X is equal to age less than or equal to 30, comma, income is equal to medium, and students are S, credit rating is fair. So we form a formula by using a training data set. Now we are calculating the probability of the training set by class values. Here we have a 0.22, 0.322 into 0.444 into 0.667 into 0.667. Here the values are the 0.322 will refers to the S value of the age less than 30, and 0.344 refers the income is equal to medium S, and 0.667 will refers the student is yes and buy is yes, and 0.667 will refers the credit rating as a 5. So when you calculate these one, we'll get only 0.044. So you got 0.044. Like this, you will calculate the probability of the X by Bayes computer no. You'll get it as 0.6, 0.4, 0.2, 0.2. So here the 0.6 will refers the age is less than 30, will have a no. And here the 0.4 will refers the income medium with a no. And here the 0.2 will no, and 0.4 will be the credit rating fair is a no. So we got the full count of the Bayes computer who are S and who are no. The values will be the 0.04 and the 0.019. Now we will calculate the probability of the X by Ci into P of Ci. So we calculate the P of X by Bayes computer is equal to S. P of Bayes computer is equal to S. So here we have got a 0.028. Now here the X by Bayes computer no into P of Bayes computer no. That comes under 0.007. Therefore, the X belongs to the class where the Bayes computers are S. So maximum we have a S or the probability of the values. So the maximum classifier will identify this as an X belongs to class. So probability of the training set data belongs to the class. Which class? That means the class where the Bayes computer are S. So the students who are ready to purchase a computer law S. So the final output of this Naïve based classifier is S. So this is the thing we got from S values. So this is the Naïve based classification. So here we have to avoid the zero probability problems. We have a probabilitical values in the Naïve based prediction. So in the Naïve based prediction it requires that each conditional probability will have a zero values. So we have to avoid those things by using this formula. For example, suppose the data set will have 1,000 tuples and the income is on a level of a 0 and the income will have medium of 990 members and the income is a high of a 10 members. So here we got the three types of the income. Those incomes are the low, medium, high. So in the low category 0 are there, in the medium category 990 are there, and the high category 10 are there. Here we have a low values will got a non-zero values. So here we have a medium and high are the non-zero values. If you are zero values are there, you are neglecting those values by in few cases only. By using a Laplacian correction, that is our Laplacian estimator, adding 1 to each case. That means income is equal to low. Low means 1 by 1003, 1003. Why 3 becomes? Why 3 came here means you have in 3 cases. So we are adding the 3 numbers in each case. So that means we are adding the 3 more categorical, 3 more values, 3 more tuples in that particular data set. So we consider it as 1000 plus 3. Why 3 means we have a medium, low, and high. So with these 3, we are adding 3 more tuples to the data set. We'll calculate the probabilitical value. So the probabilitical value, that is the probability of the income is equal to low means 1 by 1003. Probabilitical value of the income is equal to medium means 991 by 1003. And the probability of the income is equal to high means 11 by 1003. Here we have an income, low is a 0 and a medium is a 990 and high is a 10. We are adding each and every tuple will have a 1. So the income will have a 1, low here 1, medium 991, income will have a high of the 11. So the corrected probability estimates are closer to their uncorrected counterparts. So by using these, we are avoiding the zero probability problems. If you are adding a 1 by the 1, so automatically if you add 1 in the top and 1 in the low, automatically the value becomes the same. So we are adding the 0 to avoid the zero probability problems. If your 0 is there in the probability, automatically it leads in a wrong calculation. So we are adding a one more thing, that is in a Laplacian correction. So here the Naïve-based classifiers or the comments are there. We have advantages and disadvantages. The advantages will become the easy to implement. By Naïve-based is very easy to implement because by using a single formula, we are getting a Naïve-based classifier and good results obtained within most of the cases. So we'll get a maximum good results in the Naïve-based classification. And we have a disadvantages also there in the Naïve-based classification. What are those disadvantages? Means we have any assumptions that class conditionals or the independency, therefore the loss of the accuracy will come. If a class is dependent within one class to the another class, automatically we will get an accurate values within a connectivity problem, without a connectivity problem. In the Naïve-based classification, each class is an independent. So with each class of the conditional independency, we will get a loss of the accuracy in a few cases. And partially dependencies exist among all variables. So for example, consider as in hospitals, we have a patient profile, that is an age, family history, and the diseases of the families. So etc. We have a few things. And symptoms of the fever, cough, etc. And diseases of the lung cancer, diabetes, or etc. So these are all the dependencies among these can't be modeled by the Naïve-based classifier. So by basing on the one-to-one connectivity, we can't separations. For example, a family will have a few symptoms of the patients will have a family-based diseases or there. And regularly coming connectivity of the diseases are there. So if you don't have any connectivity between the independency, all are independent, so we can't get an accurate values in few cases. So how to deal with this independency of the Bayesian belief network we'll discuss, and we'll discuss in the next session, that is a Bayesian belief network. Thank you for the session and thank you.